Hi everyone, welcome back to Dragonfly Engineering. So this week we're going to wrap up the work on the custom boring bar that I made recently to help out Keith Rucker at vintagemachinery.org in turning the inside diameters of his Stoker Steam Engine valves. These are sleeves that pressed into the engine block of his medium-sized steam engine. There's been several episodes, actually, so the clips that you're going to see next are a little out of order, where I discussed when I just had these, just the raw stock of this steel. And I've already had an episode where I showed the machining of the lathe tool insert, as well as actually turning the Stoker Steam Engine valve sleeves and delivering them to Keith Rucker. But in this episode, I'm going to show the machining of the clamp blocks, and also the keyed bottom that ties into the bottom of the lathe itself. There's also some CAD that we can show, and at the end of the episode I'll show how this all fits together. And probably a few little clips of the turning of the Stoker Steam Engine valve sleeves, just for those who haven't seen that episode. But you can see the links in the description. And if you didn't see Keith's video where he was pressing these out to start with, then I suggest you check it out. I'll put a link in the description. But when he was turning these rough cast cylinders, cast iron cylinders, there was, you could probably see that his boring bar did have a little bit of flex in it. And when I was watching that kind of concerned me a little bit. He was able to get good diameters, and he actually pressed in a mandrel in the middle and used a steady rest on the outside of this cylinder, which I'm going to do the same. But after I saw the issues with the boring bar, now he did offer to send a boring bar out to me, but I basically need a heavy-duty boring bar. So what I am going to do is make my own boring bar for the track 1630 CNC lathe out there, the one that I used. Okay, and since rigidity is the name of the game with boring bars to get precise inside diameters on our valve sleeve, we need big chunks of steel. So I went to the local steel store and I purchased some rim stock. So this is cold rolled steel. I'm not sure what grade it is, but it's 2.5 inches by 4 inches by 8 inches. And this will be the bottom piece that's going to key into the existing cross slide mount on the track lathe out there. And then we've got this piece of flame cut hot rolled steel that's going to basically be the cap. And I've got the CAD model on the computer over there, and we can take a look at that in a second. But basically we're going to have a sandwich effect where this rod, which happens to be a test rod that I originally turned for the Stoker Steam Engine piston rod, you know, because I delivered 2 of those to Keith as well a few years ago. Well, this is really tough shaft steel. I want to say it's 4130, but if I got that wrong, I'll write it down in the screen what it actually is. And this is tough semi-hard steel, which is exactly what you want for a boring bar. And what's going to happen is we're going to square up these 2 blocks of steel. Oh, sorry, Sierra. And we're going to cut basically a round clamp that will hold this boring bar in position. So this piece of steel is going to basically bolt on top of this piece. This piece is the width of the cross slide mount, and I'm going to machine a keyway into the bottom of the steel to key into basically the T-nut. There's one big long T-nut that's in line with the spindle that you can put your tool holder in and everything. So we're just going to have this basically machined with a keyway tab on the bottom, and then a half circle machined into the top of this, minus a little bit. And then this top piece is going to have bolt holes and another half circle, and we're just going to make a huge rod clamp that will hold our boring bar in position. The nice thing about this setup is that I can have an adjustable depth boring bar, because basically I can just loosen the bolts on this top clamp, and then we can slide our boring bar forward or back and to whatever depth we need for this project. This is our part that we're going to turn the ID on, so we basically need enough extension to turn all this in one setup. In this case, since this is basically an engine valve part, we can't really rechuck after turning halfway in, because the real problem with boring bars is the more you stick them out, the more they flex at the end when you're trying to turn apart. So you do want to minimize stick out for basically all lathe tools. So we're going to have something like this. And the counteracting leverage of this wide clamp block is going to help make the extended boring bar rigid enough to ideally have a good cut in this cast iron. Cast iron machines pretty well. It basically makes like gray dust, but still the maximum rigidity is best since these are basically high wear engine parts. But yeah, so these are roughly the right size. I did saw, 2 inches off of this block because this came from the, basically is off the shelf, 2-inch by 8-inch by 8-inch hot rolled steel from Industrial Metal Supply, which is a local place in San Jose. Not sponsored, but they're pretty awesome. It's like a metal supermarket. And so I think we'll cut over to the CAD, and then I am going to take these blocks out to the Herco CNC with a 3-inch shell mill and square these steel blocks up so that we can then do the CNC work to make our tool holder. Oh, and then finally, I'll probably finish turning off the end of this shaft, but I'm also going to machine a lathe bit out here at the end, a carbide insert. Similar, I'm just going to copy basically the receiving feature on a carbide tool holder for the standard carbide lathe diamond bits. So we'll get into that later on in the episode. Ooh, that was a close plunge. I better check that. Alright, I think we are done with this part. I filed the edges off camera a little bit. And lift it up, and it's steel, so it still has some sharp corners, so Okay, so let's take a look at our final result here. So a few design schemes that I followed with building this was that the bottom D shape, oh, and there's still some captured coolant in there, a little rust, but so this profile is actually slightly skinnier than the rod itself, and it's slightly deeper than this rod. So the idea is that when you put the rod in, there's actually a little bit of a gap. Let's see if I can zoom in on that. Actually, I'll use the cell phone for that. So you can see there's a, I don't know, probably like a 15 to 20 thousandths asymmetric gap at the bottom of the rod compared to the sides. And the idea of having basically it tight at the sides and loose at the bottom is that, you know, this thing is sitting in our lathe cross slide, and then when our top clamp comes down, the top clamp is actually wider on the sides and more shallow on the top. And what happens is when we press this clamp down, we're actually springing out this steel block on the bottom a little bit, and we're actually wedging this drawbar into the steel block and spring loading it with a lot of force. To the point when I took this assembly back off the lathe, you know, I would take the top clamp off, and these bolts would screw into the T-slots of the lathe cross slide itself. This steel bar was still sprung, or basically spring clamped into this D profile so much that I couldn't get it off with a rubber mallet. And I didn't want to start whacking at it with a steel hammer. So I actually had to find my brass hammer and knock this bar out of this groove. And just by putting the weight of our top clamp on here, it's like jammed in again. Yeah, there we go. So I pulled it back out. So that creates a really powerful clamp, because basically this block of steel acts like a big torsion spring when you wedge this cylinder down into it, and almost like it's actually more clamping than like a Morris taper. You know, like a tool collet has a special taper and it'll lock like on the back of a lathe. It's called a locking taper. Well, this really isn't a locking taper. It's more of a spring-loaded clamp for this cylinder, a D-shaped clamp. So when I actually bolt this thing down, there's probably several thousand pounds of force just clamping onto this bar and making it super rigid. So that was a scheme that I followed. Is I played with the two D profiles to make this one pinch and this one push. And that creates basically 3 virtual points of clamp on this cylinder. And 3 points defines a plane. It also defines basically the clamp, the minimum required clamping for this cylinder. So that was a little trick I did. All right, well, thank you for watching Dragonfly Engineering. Hope you enjoyed the whole Stoker Steam Engine project saga. I think it's finally concluded, and it sounds like Keith Rucker is actually gonna do the final assembly of that engine and ship it back to the Nashville Steam Preservation Society, who's restoring a large locomotive. So that'll be cool to see. And then next episode, I think we're gonna have a major announcement for Dragonfly Engineering. So stay tuned for that, and it's gonna be big. All right, thanks for watching Dragonfly Engineering. And I'll probably lead out with some footage of this boring bar in action, working on Rucker's valve sleeves. Thanks for watching. See you next week. sleeve. The homemade boring bar. I have to scoop out more of the chips.